Okay, this morning I'm going to talk a little bit about the beginnings of packed column SFC starting around 1957 going on to 2000. It's sort of a personal memoir in some ways. Jim Lovelock had the idea of critical state chromatography, where he proposed using a polar solvent raised above its critical temperature and use it with a capillary column with a bonded stationary phase, neither one which really existed at the time, in order to separate ionic type compounds. Now, this was a pretty radical concept. Ernst Klesper, about 5 years later, actually tried to do something along those lines. He separated metal porphyrins present in petroleum with a chlorofluorocarbon as a solvent, but he used a large particle packed column, a GC type packed column with 125 to 250 micron particles. You know, today we'd think of that as huge. Over the next couple of years, C and Reinders published 4 or 5 papers on this topic, and they were the first ones to call it supercritical fluid chromatography. They were also the first to use carbon dioxide as the mobile phase. It followed on with Calvin Giddings, who was, you know, one of the preeminent chromatographers of all time, and he associated retention of the solutes with the density of the mobile phase, not with the pressure. Okay, he also published a series of allelotrophic series, a series of dilution strengths for things like dense gases. This is not really what you're supposed to do, but he gave it a try to understand how good or bad a solvent CO2 might be. We're going to talk about that in a second, but right now we'll go on to Miloš Novotný. He probably did the most extensive study of temperature and pressure in SFC to that time. And he also looked at the effect of stationary phases on efficiency. And he found that smaller particles, contrary to all other chromatography, small particles resulted in worse efficiency. And he also found that the stationary phases were these GC type phases that everybody was using, and they were not bound, they were just coated phases, and the fluids washed off the phase. Okay, and then the final of the really early guys was Buck Rogers, and he came to the same kind of conclusions that Novotný had, that you should avoid small particles and large pressure drops across the column. On the right is Giddings' allelotrophic series. And what he tried to do is calculate a Hildebrand solubility parameter for gases, for dense gases, gases at very high density, like near a normal liquid. And he came to the conclusion that CO2 ought to be as polar as isopropyl alcohol. Now, this is a huge step, because if it were true, you could start out at low pressures, low densities, and have a fluid something like pentane, a non-polar fluid, and then by simply changing the pressure density, increase the solvent strength to that of an alcohol. If that were true, SFC would have really taken off. Unfortunately, it wasn't true. And Giddings went on to change fields completely shortly after this and never had a chance to retract the series. This had repercussions for 20 years. CO2, in fact, is no more polar than pentane. Okay, in 1981, it's sort of like the modern era began. I can call it modern era, even though it was 40 years ago now. Milton Lee, with Miloš Novotný, introduced capillary SFC. This was a continuation of the previous 20 years. Now he finally could use capillary columns with bonded phases. The capillary, fused silica as capillary had just been invented, And Lee had been working for some years on bonded phases for GC, and now he could use them in SFC. With a capillary, there's no pressure drop. So he solved one of the major issues of SFC up to that time, and is no longer limited significantly in terms of efficiency. And the separations were meant to be GC-like, where they're extending GC to a heavier molecules and thermally labile type molecules. Okay, they used a very simple, actually elegant software or hardware, where basically they used a syringe pump with a GC-like oven with a flame ionization detector. And they got chromatograms that looked just like capillary GC separations with real high efficiency, but they were not programming temperature, they were programming density. Okay, even with Lee, there was a basic consensus. Pressure drops were bad, small particles were bad, CO2 had some solvent strength of IPA, and density program was the way to control retention. But right at the same time that Lee introduced capillary SFC, Dennis Geer in Avondale, Pennsylvania, Hewlett-Packard, along with two guys at HP Labs in California, came up with, started publishing papers using very small particles. And they claimed that large pressure drops were okay, as long as the outlet pressure was also high. They used small particles, so small particles were okay, but they did LC-like separations. An example here at the bottom is the separation of ubiquinones on a short 3-micron particle diameter column. I see it's 8-minute run, very simple type of chromatogram, not the complexity, not the efficiency you saw with the capillary work. What he used was a standard LC. So this was an old, early generation LC that he merely bolted a circulating chiller to cool the pump heads, and also a mechanical back pressure regulator. You can see how complicated this thing is compared to the very simple hardware using a syringe pump and an FID. The main thing that was really different was now you controlled flow at the pumps. The pumps were flow controllers, not pressure controllers. And also you can change the composition dynamically. You could actually do composition programming. Both these things were different from anything that anybody had done before. Previously, all the pumps were used as a pressure source, and the outlet pressure was not controlled. And usually the flow rate was controlled by a micro valve at the outlet of the system. So pressure was usually not, at the outlet was usually not known. And that was in fact part of the problem that people were having with back columns. Okay, well, the 1084, that was the LC that was used and converted to an SFC. It had some pros. They sold something like 50 identical units. This was essentially seeding the market, if you will, where all of a sudden people could buy something where they had control or some control of all the variables, and they could concentrate on figuring out what was going on scientifically, and not so much spending most of their time trying to figure out how to build a system. The cons of this system were it was built and meant to control the flow rate of normal liquids that have a modest compressibility, whereas HP or SFC has a gigantic compressibility compared to it. So when you try to compress CO2, you only compressed it a little bit with the machine, and then a whole lot of the strokes and everything were wasted. So you were getting much less flow than you thought you were, and you're getting a different composition than you thought you were. So the minute there's two different kinds of things called SFC, and one says one thing and the other says the opposite, you're bound to have controversies. So we wasted probably 5 years during the 1980s arguing about, which is best, which is in retrospect was a foolish thing because they're doing different things. So the questions were around Giddings heliotropic series. If CO2 is as polar as IPA, why do you want to add modifiers? Look at the complexity of the hardware. Is it worth it? Are you getting anything from it? And again, Giddings said that it was the density of the mole phase that controlled retention. So when you added modifier and you got a change in retention, it was assumed that the modifiers were only increasing the density and they were not changing the solvent strength. Both of these things were wrong, but the physical chemistry was so little understood that nobody knew that. And also the pressure drop in the system was still thought to limit plates, the total efficiency you could possibly get out of a pack column. Okay, well, everybody's arguing. Marcel Code in Paris just went ahead and separated enantiomers. Now, this was probably the single thing that made pack column SFC viable. It wasn't really noticed that much the first couple of years, but it pretty soon caught on and really made a huge difference in the technique. Almost the same time, a little bit later, we also introduced additives to the mobile phase. Up until this point, most work was done with pure CO2 or small concentrations of a polar modifier like methanol or something less polar. By the inclusion of with those mobile phases, you could only separate relatively modest polarity solutes. So strong bases, strong acids often didn't elute at all, or eluted with ugly peaks like you see at the top here. Okay, with the addition of additives, all of a sudden, the scope of pack column SFC dramatically increased. Now you could even do primary aliphatic amines, acids and bases with various additives like trifluoroacetic acid or triethylamine and a host of others. So between them, the chiral separations and the use of additives, in my book, made pack column SFC a viable technique. Okay, well, HP had put out these 50 units or so, and by 1985 they were questioning. Okay, they planted a seed. Was anything growing? What do we do now? Do we go on and build another instrument, a real instrument this time, or do we just let it go, let it drop? So they actually asked me to look into it, and I spent 4 years with some other people, and we basically did due diligence about whether or not we should build a next generation type instrument. We spent all 4 years. I visited almost everybody in Europe and the US that did pack column SFC plus capillary. We did lots and lots of experiments trying to see what things we could or could not separate. We used all the equipment that was available with syringe pumps and others. We designed a bunch of new things, electronic back pressure regulators, pumps with compressibility compensation, all that sort of things. And it took 4 years to get to the point where management could consider what to do next. And of course, they're a big company. They had tons of money. Hewlett-Packard at the time was a $25 billion a year company. They had, of course, lots of people. They had an R&D division in both the GC group and the LC group, and a third group doing mass spectrometry. So they had a vast number of experts that can be helpful. They had the infrastructure. They already make all kinds of instrumentation. They can make circuit boards and sheet metal and you name it kind of a thing. And they had very good vendor relationships. They had very high volumes so they could buy components very inexpensively. And of course, they had parts that could be used from LC and from GC that could be part of the product, so you didn't have to invent or build everything from scratch. Okay, and so in 1989, we got the go-ahead to build a new next generation instrument. The picture that's showing all the people, that's actually at the end of the process, and that's not all in there, it's R&D and manufacturing engineering. But about half of those people were on the R&D project, and there's a few missing. There's no marketing people showing there. The point of the picture is to show that this was a very serious effort and involved a great number of people to build this product. By 1992, it was ready, and we introduced it worldwide in both the United States or North America and Europe, with worldwide sales and service. And also we had full-time manufacturing engineering. So there's a whole support group that made sure we could keep the thing active and going. And of course, they had a marketing budget, the full 9 yards of a product introduction. But before we ever released the product, times have been changing. Hewlett-Packard themselves had always run the company as a research-driven organization. Most of their products were something that had been invented in the previous 2, 3, 4 years. And they were always reinventing the product line. Well, as they retired, there was a huge debate within the company. It lasted more than 10 years. And basically, at the end, the MBAs won out and decided, I call them the anti-entrepreneurs, because they do exactly the opposite of what entrepreneurs do. They stated that research is an expense, and it's an unnecessary expense for a large organization with lots of products. So the concept was they should let small companies invent, and if they're successful, buy them. Okay, and the criteria they laid down at the time was sales had to be more than $50 million a year, or it wouldn't be self-sustaining. So with those, that criteria and those kind of concepts, they sold off the SFC business after only a few years, along with 5 other fledgling products. Okay, so I guess they're expecting garage shops to start up and carry on the torch. This is a picture of Bill and Dave's, Hewlett-Packard's original garage out in Palo Alto, California. There's only one problem with this idea. A small company has none of the advantages of a big company. Got no money, no products, no cash flow from other products, no personnel, no infrastructure, no sales and service. A huge, huge deal, and no vendor relations. The only thing going for it was they had a great design, a world-class, a world-beating design. Okay, so the assets coming across were that because it had true dynamic compressibility compensation, it was the only one for 17 years. There was essentially no effective competition for 17 years. Yes, there were other companies that started SFC, packed column SFC, but they all had followed exactly the same thing that Dennis Deere did. They took an existing LC, clamped on heat exchangers, and used a circulating bath to cool the pump head, and got a back pressure regulator on the end. It had the same problems that Deere had originally, and that went on until the big companies jumped in later on. Okay, we also did the Peltier pump head temperature control, which precisely controlled the temperature, which further added to the accuracy and precision of the pumping system. We had a programmable BPR that's in many ways way more versatile than any of them that exist today. It was great at controlling pressure, but it had a lifetime problem because we discovered a new kind of corrosion, erosion that was unheard of before we accidentally discovered, and it was a big problem. We also had other things that we invented. The biggest flaw was, in fact, thermally induced noise. We had a GC type oven that was much warmer than atmospheric. And the temperature going from the column going to the detector, UV detector, was usually much warmer than the UV detector. And we had a great deal of RI noise, refractive index noise, that we didn't understand for 15 years afterwards. This limited SFC to major minor component analysis, but not suitable for QA, QC type applications. Okay, even though we didn't have any of the assets of a big company, Mark Schumann and I, two HP employees, longtime employees, we both quit our great jobs and bought the business, the HP SFC business and its assets at the end of 1995. And we found a private investor who put up this a pittance of money compared to what it takes. But he also had some other resources that we could use. Okay, so the first year of Berger Instruments was a classic startup, fitting for the point of this symposium. We took no salaries, 16-hour days, 6.5 days a week. We had an office, but it was in the basement of a converted church. And there was a lady upstairs that had a phone with different phone numbers for the different little tiny companies that were in this church. Mark sat there. I borrowed a lab from a friend. I had a dentist in the place next door to me. It was, pretty crude. Our early sheet metal was designed by a guy who designed pipe organs, high-class pipe organs for a living. And he was a very good designer, just it was pretty unorthodox. When we finally started getting parts to assemble, Mark Schumann, the CEO of the company, did the assembly. He had some help, but he did the assembly for the first 15, 20 units. And I did the chemical checkout, making sure everything was working properly and uniformly with all the other units. We hired our first salesperson, and I spent most of my time evangelizing, trying to talk to anybody that would listen, that SFC was a great thing and they ought to buy one. Okay, we had this one huge advantage. Without it, we would have failed miserably. And that we inherited this exceptional engineer. Okay, in the very short time that SFC, Berger SFC existed, we built quite a few different products on the analytical scale, and we became the first people to have successful semi-preparative SFCs. In the process, we invented stacked injections. We injected modifier stream injection. We built the first commercial chiral method development system on the analytical scale. So you could choose the best column and the best mobile phase, which scaled directly into the semi-prep units. We also built a number of different gas delivery systems that feed the CO2 to the instrumentation. Now, what's surprising is this is still the Achilles heel of SFC uptake by a large number of corporations. The infrastructure required adds expense, and it's different from LC. And because of that, it slows down all the processes. Anyway, you would think because we built so many different products that somehow it went very easily and it was just natural. Well, it was anything but. Most of the time we were within a month or two of going out of business. We had to grow. We had to satisfy the new demands that the customers kept coming up with. The minute we had chiral method development, people wanted a semi-preparative machinery. And nobody was giving it to them, so it was up to us. Okay, so many problems came up, many things that almost put us out of business. One of the worst was our best customer, without any warning, told us, we'll never buy another thing from you until you have a 62-bit software. Well, surprise. It takes 20 to 30 engineers years worth of work to build a chem station. And of course, we have a SFC chem station, which is different from other chem stations, and you can't buy one. So suddenly we're supposed to somehow magically create a SFC 32-bit chem station. Well, this, obviously created panic, and we called in every kind of help we could get, and we managed to make it work, but it took months, and it really disrupted all new product development. But we managed to make it work. We went on. Why'd it work? Well, we had a compelling application. The chiral. We decided that was the key before we ever decided to buy the business. It's still the thing that's driving most of what SFC, most of what it's used for. We had obvious product superiority because we had big company engineering in a little company. All this was absolutely mandatory. And we then, once we had this engineering, we very aggressively developed new products to exploit it and expand the characteristic of the product line. So by the end of 2000, we had 43 people in the factory, 20,000 square feet for manufacturing and labs, direct sales and service to both North America and distributors in Europe and Japan. The European distributor was very closely held. And it was, altogether, there were probably 80 people involved, something along those lines. At the end of 2000, we were suddenly and unexpectedly approached by both Waters and Mettler Toledo, who wanted to buy the company. Well, we had a contract still with Hewlett-Packard, who was still supplying some of the bits and pieces that went inside of some of our boxes. And we had a contract that said that we couldn't sell to a competitor of Hewlett-Packard, so that left Waters out. So we talked with Mettler Toledo, and we made a deal. We sold the company to them. I think it went through in 2001. We stayed on to manage the company for another year and a half, sort of the transition. And then it became part of Mettler Toledo, which eventually sold it to FAR, who sold it to Waters Corporation. Okay, today there's quite a few vendors on the analytical scale. There's 4 major vendors, 3 of which do compressibility compensation. And there's worldwide sales and service because these large companies, they sell all these other things too, LCs and GCs and mass specs. So all of a sudden customers have the reliability of buying from a large company. The thing that's been new over the last, say, 5 years is that SFC has now been shown to be just as sensitive as HPLC in terms of trace analysis. So SFC has now been validated with a multi-lab, multi-vendor testing using sub-2 micron particles with gradient elution on a pharmaceutical formulation. First time this has happened, and now SFC is now being used more and more in QA and QC type applications. Chiral is still the technique of choice for both method development and purification, but the world is expanded. Anyway, to me, that's the end of the beginning. Thanks for listening.